thinking more about forces, here's the most important thing we know about forces. It's Newton's second law. It makes explicit the connection between force and acceleration that we've been talking about all along. That forces are the things that cause acceleration, and usually there's more than one force acting on an object at any one time, so you have to see whether all those forces add up to some kind of force or cancel each other out. I mean, obviously, in this case, I'm holding the pen. The pen feels a gravitational force, weight, but it doesn't accelerate because there's another force, the upward force from my hand, which turns out to be a normal force that cancels out the weight force from my pen. The net force in this case is 0, so the pen does not accelerate. But anyway, we know that if we add up all the forces acting on some object and the net result is force, that is, the net force is not 0, then the acceleration will not be 0. It must accelerate, because if there is force, there must be acceleration. Force is what causes acceleration. And similarly, if we observe that an object is accelerating, and we observe that its acceleration is not 0, then we know for sure it's accelerating because it feels a net force. That the net force on it is not 0. Now let's one aspect of this this equation here is the vector aspect. That's an important thing to remember. Remember earlier when you're reading through chapter 3, and in the first section it was described this operation called multiplying a vector by a scalar, multiplying a vector by just a plain number. And that, of course, is what you're doing here on the right-hand side of the equation. You're taking a vector, net force, and multiplying it by a plain old number, 1 over the mass. And as you saw described in chapter 3, when you multiply a vector by a plain old number, a scalar, you get a new vector, and this vector turns out to have the same direction as the net force. Furthermore, here in Newton's second law, you've got a vector on one side of the equation, a vector on the other side of the equation. In order for two vectors to be equal, they have to have the same magnitude, they have to have the same size, but they also have to have the same direction. If they're not pointing in the same direction, they are not equal vectors. So the direction of the acceleration is the same as the direction of this vector, 1 over mass times net force, but the vector 1 over mass times net force have the same direction as the net force. So the moral of the story is the direction of acceleration is the same as the direction of the net force. Acceleration points in the direction of the net force, which kind of makes sense because it is, after all, the net force that causes the acceleration. The acceleration points in the same direction as the thing that caused it, net force. So let's just add that to something we already know about the direction of acceleration. We know that if something is speeding up, then velocity and acceleration point in the same direction. And now we know that that acceleration was caused by a net force, and the net force points in the same direction as the acceleration. So you could just as easily say that if something speeds up, velocity and net force point in the same direction. Or similarly, if something slows down, we already know that velocity and acceleration point in opposite directions when something is slowing down. But again, we know that that acceleration is caused by a net force, and the net force points the same way as the acceleration. So you could just as easily say, when something is slowing down, velocity and net force point in opposite directions, which makes sense. If you're moving in one direction and slowing down, it must be because there's something pushing or pulling backwards on you. And then if you're speeding up while you move this way, it must be because there is something pushing or pulling you in the forward direction. So that's the important vector and direction part of Newton's second law. Let's just think about magnitudes now, magnitudes of net force, magnitudes of accelerations. That is, the magnitude of the acceleration is just the magnitude of the net force divided by mass. And let's imagine now that we're applying the same net force to a bunch of different masses. So, for one mass, we'll call it M1, you get one particular value of acceleration, that's just net force divided by M1. And we'll say that acceleration 1 has a value of 2 meters per second. Meters per second, I mean, the magnitude of that acceleration, 2 meters per second. Now, let's imagine that we have twice as much mass. So there's a new mass, call it M2, which is just twice as much as M1, and that's going to give us a different acceleration. The magnitude of that new acceleration is A2, which is the same net force divided by the new mass, but the new mass, we could also just call it 2 times M1, because that's how big M2 is. Or F net over M1 times 1/2. But of course, F net over M1 is just the magnitude of the first acceleration. So what we have here is the first acceleration times 1/2. That's the magnitude of the second acceleration. Now let's try that again. Let's say we take a mass that's now 10 times bigger than the original mass. Call it M10, which is 10 times M1. So that gives us a new acceleration, we'll call it acceleration 10, and the magnitude of that acceleration 10 is just magnitude of the net force divided by m10, but m10 is just 10 times m1, but this part here, net force divided by m1, is just the first acceleration, a1, or the magnitude of the first acceleration. So we have here acceleration a1 divided by 10, or times 1/10. So a10, the acceleration that you get by applying the same amount of force as always to 10 times more mass, is just 1/10 of a1. That was a1, so a10 is 1/10 of that, 0.2 meters per second per second. And then just one more here, and then we'll see pretty clearly what the pattern is. Now, instead of taking bigger masses, let's look at a smaller mass. We'll call it m1/5, because it's just 1/5 as large as m1. So the acceleration that you get, we'll call it acceleration 1/5. The acceleration that you get by applying the same force as always to that new mass, m1/5, is just the same net force as always, divided by the new mass, m1/5, which is just the same net force as always. m1/5 is just 1/5 of m1. And again, this part here is just acceleration 1, and divided by 1/5, which is the same as multiplying by 5. So we have magnitude of a1 times 5. So the acceleration with 1/5 as much mass is 5 times a1, or 10 meters per second squared. So here's the pattern that we see. So new mass is twice the old mass. That means that the new acceleration was half of the old acceleration. And then the new mass is 10 times the old mass. That implies that the new acceleration is 1/10 of the old acceleration. And then finally, new mass is 1/5 of the old mass. That implies that the new acceleration is 5 times the old acceleration. So what we have here is an example of a particular kind of relation between variables called inverse proportionality. Right? In this case, the variables are the magnitude of the acceleration and the mass. Every inverse proportionality relationship has the same form, and it looks like this. One variable equals constant factors divided by the other variable. So one thing you see there, in any inverse relationship, if x gets bigger, y gets smaller. If x gets smaller, y gets bigger. In an inverse proportionality, whenever one variable increases, the other one must decrease, and we saw that here. When you went from the first mass to the second mass, the mass got bigger and the variable that it is inversely proportional to, the acceleration, got smaller. And going from mass 1 to 10 times more mass got bigger and the acceleration got smaller. And then going from 1 mass to 1/5 as much mass, the mass decreased, and so the acceleration increased because the acceleration is inversely proportional to the mass. We can be a little bit more precise about how much something increases and how much something decreases in inverse proportionality. And the rule, you should keep this rule in mind, learn it. It's that when one variable changes by a factor of, let's say the factor n, change by a factor of n just means we multiply it by n. So I write it as times n. So when one variable changes by a factor of n, then the variable that is inversely proportional the inversely proportional variable also changes by some factor, a factor of 1 over n. Changing by a factor of 1 over n just means it is multiplied by 1 over n, so I write it as times 1 over n. And now you see what's going on here. Just think of n as something greater than 1, so when one variable changes by a factor of times n, it increases. And then the variable that it's inversely proportional to changes by the inverse factor, so it decreases. And that's exactly what we saw here. One variable, the mass, changed by a factor of 2, so the acceleration changed by a factor of 1/2 because mass and acceleration are inversely proportional. And then if mass increases by a factor of 10, then acceleration, being inversely proportional to mass, must change by a factor of 1 over 10, decreases. And then if mass changes by a factor of 1/5, acceleration must change by the inverse factor, 5. When one variable changes, the other variable changes by the inverse of that factor. That's inverse proportionality. And it turns out that these proportionality relationships are useful very often. They help us to understand how one factor depends on another factor, and even help us to calculate values in situations where we think we might not have enough information. For example, let's say some mass has an acceleration with a magnitude of 1 meter per second, and some amount of mass that we call m1 has this acceleration, 1 meter per second. Then the same force is applied to, let's say, just 1/3 as much mass. So the second mass, or the new mass, is just 1/3 of the old mass or first mass. Well, Mass and acceleration are related by Newton's second law. And Newton's second law looks exactly like the general form for any proportionality relationship, where this variable y corresponds in this case to magnitude of acceleration, and the other, the variable x, corresponds to the mass. And the constant factor here that's in the numerator corresponds to this factor, which is constant because we're applying the same force to all kinds of different masses. Right? Same number here, all kinds of different values here. So now we know how inverse proportionality works. Well, when one variable changes by some factor, the other variable changes by the inverse of that factor. In this case, one variable, the mass, changed by a factor of 1/3. So the other variable, magnitude of acceleration, changes by the inverse of 1/3, which is just 3. So the new magnitude of the new acceleration is just 3 times magnitude of the old acceleration. So 3 meters per second per second. In this case, we're able to come up with a number for acceleration, even though we did not know the actual value of these masses. All we knew was that one mass was only 1/3 as big as the other mass. We didn't know the actual values. And we did not know the value of the net force. All we knew was that the net force stayed the same. And that was enough to allow us to use proportionality reasoning to figure out what the new acceleration looks like. And you'll be doing a lot of that kind of thinking, proportionality reasoning, as the semester goes on. But one important thing about all this gives us a better idea of what mass actually is, what mass actually measures. In the previous video, I said, warning, mass is not weight. They're two different things. Weight is a force. Mass is something very different from a force. Now we have a better idea not just of what mass isn't. It isn't a force. We have some idea of what mass actually is. Mass is inversely proportional to the acceleration if everything is feeling the same net force, if the net force is constant. In other words, when mass increases, acceleration decreases. That's what we saw in all these examples. The more mass you have, the less acceleration you get for any particular amount of force. So what mass measures is an object's ability to fight against a force. It measures an object's ability to resist being accelerated. And that ability of an object to resist being accelerated we call inertia. Mass is the quantity of an object's inertia. More mass means it's more difficult to accelerate. More inertia. Less inertia, in other words, less mass, means it's easier to accelerate. And any particular amount of force will give a bigger acceleration than you would get if you applied that same force to a greater mass, which has more inertia and is better able to resist getting accelerated.